Magnetic force on a conductor. So when we say a conductor, we're referring to just simply a wire that electrons flow through or electricity flows through. So what we're going to set up here is I have this horseshoe magnet with a north and a south side, and I'm just going to put it on its side. So any magnet, we have magnetic field lines that go around it, always from the north to the south pole. So there's actually a magnetic field going from the north to the south right here. And what I'm going to do is I'm going to put a wire just inside that magnetic field. So this is a conducting wire. Now, a very cool thing happens. If I hook up this wire to a power source, when I flick it on, well, when current goes through the wire itself has its own magnetic field around it. So it's almost as if I've taken north pole of a magnet and north pole of another magnet, and what will happen is it'll push it away. And that's exactly what happens here. So when we have a magnetic field from the magnet and it interacts with the magnetic field just because there's current running through the wire will do one of two things. It'll either push it out or pull it in. And all it depends on is which way is the current flowing through the wire. So again, two things will happen. One of two things will happen. It'll either push it out or pull it in. And we can figure out how far it'll go and which way it'll go very, very easily. So let's get to the note. So here's my diagram of basically what I was trying to demonstrate to you. So if you have a north pole and a south pole, well, there's magnetic field lines that go from the north to the south. If you put a wire through those magnetic field lines and you run a current through it, well, all of a sudden it's become a magnet as well. Okay, and it's going to push that wire either up or down. And if you wanted to figure out what that force is, well, we have a very simple formula. Okay, it's ILB sine theta. So it's how big the current is, how long the wire is, how big the magnetic field is, like the outside magnetic field, times sine theta. Now, this is important about theta. If an angle is not given, always assume it's 90. Always assume it's going in at 90 degrees. If it's going in at an angle, so what that means is instead of being perpendicular like this, okay, it's kind of cutting across on an angle. So instead of being perpendicular, it's cutting across. So always assume it's 90 degrees unless told otherwise. And we know what most of these are. So F is just the force on the conductor because the wire physically gets pushed. B is the magnetic field, and that's measured in Teslas. I is the current in the wire or the conductor, and L is how long that conductor is. A straight conductor 10 centimeters long with a current of 15 amps moves through a uniform 0.6 Tesla magnetic field. Calculate the magnitude of the force on the conductor when the angle between the current and the magnetic field is 90 degrees, 45 degrees, and 0 degrees. So first thing we should do is write down all the things that we know. So it says that the length is 10 centimeters. So I'm going to go L equals 10 centimeters. And we need to convert that to meters. It'll be 0.1 meters. We know the current is 15 amps. The magnetic field B is 0.6 Teslas. And we're looking for the force on the wire. So what we're trying to find is, well, when the two magnetic fields interact, how hard is this wire being pushed to the side? So we're looking for the force as a result of the two magnetic fields interacting with each other. So our formula is F is equal to ILB sine theta. And we just plug in everything that we know. So it'll be 15 times 0.1 times 0.6 sine 90 degrees. Now, whenever you have sine 90 degrees, that's just 1. If you think about the sine graph at 90 degrees, it's at the maximum, the peak, 1. Plug that into your calculator and you end up with 0.90 newtons. Force is always measured in newtons. In B part, The only thing we're going to change is the angle now. So let's do that. So we write our formula. So it's just force is equal to ILE sine theta. All the information is the same except for the angle. So it'll be 15 times 0.1 times 0.6 sine 45. So that means instead of the wire being perpendicular, it's on an angle of 45 degrees. When we put that into your calculator, you end up with 0.64 newtons. So what's interesting about that is it has a greater force when it goes in perpendicular to the magnetic field lines. If it's on an angle, the force is actually decreased. Well, if we have a 0-degree angle, so that means instead of it being perpendicular, it's parallel with the magnetic field lines like my pen. So instead of going in perpendicular, it is parallel. So if we put all our information in, we have F is equal to ILB sine theta. And again, the only thing changing now is the angle. So 15 times 0.1 times 0.6 sine 0. Well, sine is 0 is actually 0. So 0 times anything is just 0 newtons. So when the magnetic field lines line up with the conductor, we don't get any push, we don't get any force. So to maximize that force, we actually want to be at 90 degrees.